Okay, welcome to today's lecture on perceiving movement and vision and actions, how those interact with one another. We're going to start out today by sort of reviewing a little bit about perceptions, right? So, perceptions are a creation of the nervous system, right? And we talked about that with colors, how colors are created by the nervous system. And perceptions are more than just sensations, right? Gestalt showed that, right? That it's more than the sum, that we have top down influences that are adjusting the sensations as they come in. Perception involves interaction between different systems, both within that sensory system and with other sensory systems. We haven't even talked about the other sensory systems yet. We've just been focused on vision. But within vision, we can talk about the dorsal stream and the ventral stream and how they interact with one another. And we'll talk about that today some more. And then finally, perceptions are based on heuristics often. So we're using these commonly found principles to organize and speed up our perceptual ability. All right, so turning towards motion perception. There are four ways to create motion perception. You can have real movement. So an image moves across my retina, and I'm going to perceive that as movement due to movement of the object in the environment. Right? We can measure the threshold for detection of movement, and we can measure that in visual degrees. It's about a sixth to a third of a visual degree per second. And so if we were to have something that was 1 foot in front of us, if we didn't have any other cues, we just had real movement of that, it would have to be moving faster than 1 inch every 11 seconds. So if it moved 1 inch in 10 seconds, right, we wouldn't perceive that thing as moving. But we don't perceive movement without other cues, right? So what is probably one of the biggest cues or heuristics we use to tell that something's moving in our environment? We already talked about it when we talked about depth perception, right? Accretion and deletion. The fact that when something covers up something behind it and then uncovers something, that's a strong cue that that thing is moving through our environment. All right, so take a look at this screen. This is affectionately called the snake illusion. And I want you to find a part of the screen that's moving, and then I want you to put your finger on it. And when you put your finger on that part, what happens? It stops moving because this is a static image. You can print out the slides and look at it. It's not a trick. It's actually not moving. So what's happening here? Well, this is called apparent movement. It's another way to create motion perception. And this is due to the complexity of this image. Our eye can't keep track of where all the different parts are. And so it appears that they're moving. We talked about apparent movement also when we talked about the stroboscope, where if you flash two lights and you vary the onset, the interstimulus interval, the time in between each one, if there's sort of a sweet spot, depending on how far apart they are. So if you flash them too quickly, then it looks like they happened at the same time. We can't tell that there's a delay. If we slow down and make that delay a little bit longer, you start to get movement, either partial movement or when you get in the right ability to, the right time in between those, you actually start to see smooth movement or illusory movement. And then as we make the time even longer, it becomes successive, right? It's one flash happens and then the other one happens, and we don't perceive that movement anymore. So that's real movement and apparent movement. The third way is induced movement. Movement of another object induces the perception of movement. You've probably experienced this if you've been on an amusement park ride where you're seated and the screen, everything is moving around you, but you're really not moving that fast or moving at all. You're just being tilted one direction or another. That's an example of induced movement where you feel like you're moving through the environment, even though it's the environment moving around you, right? The moon appearing to race through clouds, where the clouds are actually inducing the movement of the moon. The moon's really not moving that fast across the sky. It's the clouds that are producing that. Vection is actually the vestibular feeling where you feel like you're moving because there's movement in the environment. So if you've ever been sitting in your car at a stoplight and there's a big tractor trailer beside you, and the tractor trailer starts to move and you push harder on your brake because it feels like you're moving backwards, that's vection. Right? And then the fourth way is movement after effect. This is an adaptation response through overstimulation of the receptors. So maybe you've seen this if you've been scrolling through a website and then you stop. It looks like the words move in the opposite direction, right? I can show you really cool illusion here. Okay, so what I want you to do is look right in the center of the spiral. Keep looking right in the center of the spiral. No, I'm not trying to hypnotize you, but keep looking. Keep looking right in the center. And when I tell you to, keep looking. When I tell you to, I want you to look at the back of your hand. Okay, look at the back of your hand. Wow, that's pretty weird, isn't it? So it looks like your skin's moving, right? Because of adaptation, right? So that's movement after effect. All right, so how do we detect movement? How do we do this? How do neurons detect movement? In particular, what sorts of features are neurons detecting? We've already talked about V5 and middle temporal cortex being involved with movement detection, right? The magnocellular pathway, superior colliculus helping us orientate our eyes to movement in the environment. Even in V1, we talked about complex neurons there. So how does this movement signal get created? How can we have directionally specific movement in V1 at that level, at the first level of the cortex? And it turns out that the amacrine cells are doing yet another thing in the retina, another type of processing to generate real movement signals, right? So if we have a bunch of receptors here, you can see, so A through F, right? We can hook them up in a way that when something moves from right to left, right, we're going to stimulate the F, it's going to generate a signal, stimulate E, it inhibits that signal, stimulate D, right, and B. So this neuron M would only fire when something's moving right to left. If something were to move left to right, it's going to stimulate A, which is going to inhibit H. So when B gets stimulated, it's already being inhibited, and so forth with this inhibition, right? There's a nice, we'll talk a little bit more about this in a minute, but there's a nice web activity on the textbook website where you can kind of play around with speed and see how the speed of movement can even be coded in the retina. Okay, so where is motion detected? So we can use that principle of adaptation to show, using the motion after effect, to show that there are motion sensitive areas of the brain. If we stimulate them, their tuning curves shift, and we see the opposite motion when we stop. So here, let's turn the speed up just a little bit. So focus on the white cross there, and the dots are all moving up, right? And what happens now? They're slowly drifting down, but actually they're not moving. You can put your finger on the screen and see that they're not moving, right? And if we now go, if we now go to the right, we're adapting our middle temporal cortex. And now the dots are slowly moving backwards, even though they're not moving at all. Okay. So we know that there's some primary areas that are involved. we have complex cells, direction-specific movement in V1. We also have V3, which is responding to movement, and then we get into the middle temporal cortex. And the middle temporal cortex responds to directionally specific movement. That's why we see that motion after effect, the adaptation. And if you remember, we talked about this when we, in the first section, when we started talking about different areas of the vision cortex and what do they do in the extrastriate cortex. And we said that monkeys with an intact middle temporal cortex only need 1 to 2% correlation of movement to be able to accurately detect which direction those things are moving. And the benefit of doing this with monkeys, obviously, is that we can go in and then measure the neural activity and see, okay, how much neural activity is generated by 1 to 2% correlation of movement. And so here, if we look at the blue line, that is the monkey's performance on accurately saying which direction the randomly correlated the dots within the randomly correlated dots are moving. Right? The red is showing the firing rate of the neuron. Right? And so as that motion sensitive neuron fires more, the monkey has a better percent correct. So the perceptual ability, the point of this is the perceptual ability directly follows the neural activity. Less neural activity, harder to make a correct decision. More neural activity, easier to make a correct decision. If we then go into the monkey and lesion, right, then we see that we need almost 100% correlation of movement in order to detect the movement. Here we see a brain damaged patient who had a stroke in their middle temporal cortex, right? And again, they need almost 100% correlation in order to detect the movement, whereas normal people need very little correlation of movement. All right. So if we go in and record from a neuron that has a preferred direction of movement, right? And we look at the neuron's baseline firing rate. So here we have 0.8%. We're not able to, perceptually, we're not able to detect which direction the dots are moving over here, right? If we increase that correlation and make more dots move in the same direction, here's what happens, right? We start to get in red, that would be what's shown here, moving from left to right, right? The neuron starts, when the dots are moving in that direction, the neuron starts firing a little bit more. So the baseline firing rate, it's firing somewhere between 20 and 50, with 30 and 40 spikes per trial, about the same. So now, if we move in the opposite direction, from right to left, we start to get a decrease from baseline firing rate, right? And then as we make even more dots correlate, it really separates out so that when the dots are moving from left to right, which is this neuron's tuning curve, its preferred firing rate, we go from a baseline firing rate of around 40 up to firing around 80 or 90 times, right? And if it moves strongly in the opposite direction, we go from that 40 and we have an inhibition, and so we now reduce from baseline when it's going the opposite direction. That's in a monkey, obviously recording from a neuron, but we can measure this in people as well with MRI, with functional imaging. And here we have the stimuli are a blank screen, moving dots in a specific direction, or stationary dots. And if we look at firing in V1, V1 is firing to all the stimuli. It's firing to stationary dots, it's firing to moving dots. But if we look in middle temporal cortex, it is only firing when the moving stimulus is present, right? So now we've separated out the movement aspect from V1 through V3, V5 into middle temporal cortex, where we have this very directionally specific movement. All right, so there's a problem, sort of like the inverse projection problem, with detecting movement. So the problem is we can have multiple things produce real movement on the retina. So, for instance, if we have a stationary object, right, and I move my head or I move my eyes, I scan across the scene, right, then my hand is moving across the retina, but my hand is actually stationary, right? And if I were to follow an object like this, right, then that object is staying stationary on my retina, but my eye is moving, right? And because my eye is moving, but I actually perceive that object as moving, not as stationary, right? So how do we do this? Well, we actually have a system set up to compare real movement across the retina signals with eye movement signals, right? So we're comparing this from two different pathways. This is called the corollary discharge theory. So we have two inputs. We have a CDS, a corollary discharge signal, which is the motor signal. It's telling us information about how my eye is moving, right? And then we have the real movement signal, the image movement signal, the IMS, the sensation of something moving across the retina. And both of these signals come in to an area of the brain we're going to call the comparator that is going to compare, right, the CDS and the IMS and send an output that's either movement or not movement. Okay? And it's pretty simple how it does that. When the CDS and the IMS signals do not match, meaning there's activity in the CDS but no activity in the IMS, we perceive movement. Or there's no activity from the eye moving, but there's real movement signal, then we perceive that as movement when they don't match up. If they do match up, right? So I have, I'm moving my eyes, right? And there's real movement because I'm scanning through the environment. Those match up. So we have a signal of real movement and we have a signal of eye movement. That would tell me that the thing that's moving is me and that everything else is staying stationary, that there is no movement, right? All right, so let's think about how this works. If we were in the classroom, I'd draw you a nice picture like this, but this will work well. I've animated it a little bit. So we have our eye movement signal, a motor signal coming into the comparator. We have these direction-specific movement signals coming in from the retina, the IMS, right? If they don't match up, then that signal gets routed from the comparator through from V1 through V3, V5, MT, and that's our dorsal stream, our movement processing stream. If they do match, however, that signals that there is no movement. Then its signals getting routed from V1 into V2, V3, V4, IT for our identification of that object, and we don't perceive that object as moving. So going back to our processing signal, how do we generate that real movement signal coming out of the retina, right? If there's a point of light here, right, it's going to stimulate the green and brown neurons. It's also going to stimulate this inhibitory neuron, which is going over to the next screen. So as that moves across here, only the brown neurons are being activated because the inhibition from the previous neuron is keeping the green from being activated. So we generate a left to right signal. Now, if we want to move back the other way, right, we start over here on the right, there's a blue neuron. So the green neuron gets activated and the blue neuron is going to inhibit the brown now, right? And as we move back over, the blue neurons are keeping the brown from firing and allowing the green right to left signal to come in. All right, so let's talk about 4 different situations in which the CDS could produce perceived movement without the IMS. Okay, so if you move your images while viewing an after image in the dark, right? So an after image would be, so say someone takes a flash picture of you, and there's big flash, right? You bleach that area, and for a little while, there's a little white dot, right? So if you look around, that white dot looks like it's moving, it's floating around, because that area of the retina is staying activated, it's staying in one spot, right? So the after image always stays in the same place, but your eyes are moving. So those signals don't match up, right? So we should perceive movement. And that's what happens. It looks like that dot's moving, floating around in the environment as you move your eyes, right? Here's a fun one we can do. So if you close one eye, so you only have one eye, and then you gently push against your, not your eyeball, but under your eyelid, right? And kind of push your eyeball, you perceive the environment is moving, right? Because your eye is staying still, but by pushing on your eye, you're generating a real movement signal, right? If you follow a target, right? So something's moving through my environment and I'm following it, right? That image is staying in the same place, so no IMS signal, and there's but my eye is moving, so they don't match, so we would perceive movement. All right, so here's a tricky one, right? What if we paralyze been a long day, paralyze the eye muscles and try to move our eye? What, are we going to get a real movement signal? No. Are we going to detect that a signal was sent to move the eye? Yes. So in that case, we're going to perceive movement in that case. All right? All right. So there are neurons in V3 that are sensitive to real movement, not just IMS. So when I say real movement, I mean the output of the comparator, right? So here in a monkey, we have them fixate on a point, and then we're going to move this bar through this V3's receptive field. And when we do that, it fires strongly, right? But now we can generate the same signal by having the monkey move his eye across that bar, move his receptive field now down across that bar. That would generate exactly the same retinal signal coming out of there, right? But the monkey perceives movement in the first case and not in the second case because of the eye movement, right? So because the eye is moving and the image is moving across the eye, that's a no movement signal because they match up. If there's damage to the middle temporal cortex, it will impair our ability to detect movement, and that's called movement agnosia. All right. So movement and object perception. We already talked about how we can use movement. We talked about a Gestalt heuristic where we use movement to help us identify objects. So which one? We'll do an Ed puzzle real quick. All right, so hopefully you remember that common fate is one of the 6 primary Gestalt principles that uses movement to help identify objects. And we can see that here. Right? And so if I start to move this, now you can see an airplane shape, but if I stop moving it, it's very hard to detect that, right? That's common fate because I'm moving these all together, they belong together, and we can clearly see the object. As soon as I stop moving it, right, it goes away. Biological movement is a heuristic that looks for movement that belongs to certain animals or people, right? So we can look at this example. And we'll talk about this more in a few minutes. But here, you perceive these balls of light as a person walking, swinging their arms walking, biological movement. Movement can also add dimensional characteristics to a 2-dimensional image. So movement can give us a 3-dimension perception. So here, if you look at this silhouette that's moving, right, you either see it as rotating from left to right, or you can see it rotating from right to left, right? So Figure out which way it's rotating for you, and then let's try for a few seconds to make it move the other way. Were you able to reverse it? How about if I add in these spheres? Right? So if I turn on the lighting and we remove the silhouette effect, then we unmask that and we see how the object is actually moving the whole time. Okay. And then finally, motion capture is where smaller elements within a larger figure all move together, therefore they all belong together. So you can think about the image of the Dalmatian dog that was sort of masked by, in that black and white image that I showed last week. If that dog moved, all of the dots on the dog would move together and it would be very clear where that object was, motion capture. So let's look at biological motion in a little greater detail here. All right, so if I show you this picture here and ask you what it is, and I show you this picture here and ask you what it is, right? If I could make those move, right, you could say, okay, that's somebody walking, and this is somebody running in the opposite direction. And the points of light that we need to be able to see, right, to perceive this movement, biological movement, are at critical places: the shoulders, the head, the elbow, the wrist, the hips, the knee, and the foot, right? So here we have a person walking from left to right. What do we have here? What do you perceive? A person walking backwards from right to left? Okay. So some other heuristics of movement is that movement generally continues in the same direction in the smallest or simplest amounts. So if I show you that X moving, most people perceive that X as moving clockwise, because we tend to perceive clockwise movements first as simpler before we perceive counterclockwise movements. But the X only rotated, it rotated the same amount in both directions, right? So you could potentially perceive that as moving counterclockwise. If we now show you this rotation, now we've moved that object in smaller increments clockwise, and so it's very difficult to see the image as moving this way, right? As moving from here to here. Okay. Occlusion, right? Sort of like accretion and deletion, right? Says that a moving object will cover and uncover the background, right? Accretion and deletion. And so if I have a triangle and a square, and I make them move back and forth like this, it looks like the square is moving up to the right, and it looks like the triangle is moving under the square, right? That effect becomes even greater if I were to put a box in there, right? Now, instead of appearing to move, and that's really flashing too fast, but I can't make it go any slower. Instead of appearing to move, the ball to move up and underneath the other ball, it looks like it's moving under the square, that the square is occluding it. We can also have meaning and movement interaction. So there's crosstalk between that middle temporal dorsal and the IT ventral pathway to help identify objects and identify objects' movements, right? So there's a dependence between the two separate pathways. Remember when we talked about dissociations? Oops, that was really quick. Let's see if we can do that again. All right, so what did you perceive there? Look down in this area one more time, okay? How about over here? So if I slow it down, it looks, in the first one, it kind of looks like there's a head that rotates, right? The second one you see, because we slow it down, you see that even stronger, right? You're able to perceive the face, the two faces, and you assume that one moved in a certain way to become the other one. We have some other heuristics of movement, like the shortest path constraint. It says that movement tends to occur on the shortest pathway. Now, that shortest path can be overridden if it violates other meaningful heuristics. So if I show you this picture of this woman with her hand behind her head, and then all of a sudden her hand is in front of the head, right? You don't perceive that hand as coming through the head, right? Because that doesn't happen, right? And so if I go back and forth, if I can make this happen, if I do it too fast back and forth, then it does look like the hand is popping through the head. But if I do it at just the right stimulus interval, then it looks like the hand is moving around the head, even though there's never an image of the hand over here. It's just here or here, but it looks like the hand is moving around the head. So a couple of things we can take away from that. One, the visual system needs time to incorporate meaningfulness, right? If I make that hand go too fast back and forth, then we know you can't move a hand around your head that fast, and so it must be coming through the head, right? And special characteristics of the meaning, like the fact that if I have my hand here and I come around here, that it takes about 200 milliseconds to do that. And if we flash those two images at that same rate, then we perceive, because of the meaning of someone's hand behind and in front of their head, we perceive that apparent motion, apparent movement there. All right, so we want to start thinking a little bit more globally about vision and starting to sort of put all this together and move towards how do we use the perception of movement for us to be able to do actions to move through the environment and not run into things and that sort of thing. So if we talk about the ambient optic array, the optic array is everything that's hitting our retina, right? And it can be static, as it's shown here in this image. And we use heuristics to fill in the pieces that we can't see. So everything with a dashed line is not in this person's optic array. Everything with a solid line they can see. But we know, by sitting here looking out this window at this truck, that this truck has a tire. And we know we can estimate the general shape of the front of the truck because we have heuristics of what trucks should do, right? I have a heuristic that there's going to be a square angle here and that this isn't a rounded curved ceiling, right? Even though I can't see that, my heuristic is that it is a straight. And as we move, we use movement to sort of fill in. If we have a heuristic that we don't really know the answer to, right? If we stand up, then we can change our optic array to fill in those parts. So we talked about optic array when we talked about accretion and deletion of the optic array indicates movement and depth of objects, if something's in front of or behind an object. It can also be used in movies to produce the illusion of movement. So as this man is walking down the sidewalk, his body is deleting parts of the scene behind him and accreting or creating parts as he moves through there. Movies use this with green screens, where now we have 3 cameras that are filming the front of this car as they're supposedly driving, and we're going to put movement behind them. And as parts of the car delete and accrete it, we're going to see that movement and perceive them as moving, not as the background moving. All right. So we use these signals not just to detect other people moving, but to help us moving through our environment. And we call these, when the optic array begins to move, we call that optic flow. Optic flow. So when the optic array is in motion, we have this optic flow, we have motion parallax that is going to say that objects that are closer to us are going to move faster than objects that are further away. Furthermore, right at the center of our fovea, it appears like there's no movement, and this is the focus of expansion. It actually looks like things are expanding from that point. So we can see this in this this static bridge example, the focus of expansion, and these things closer to us are moving faster, but we can see it even better if we look at this. So as an object gets faster, closer, it speeds up, right? And so way out here, those railings or the street lamps are moving pretty slow, but if we look at them, if we just focus on this part, they're moving much, much faster. And then we have a focus of expansion down here that looks like it's not moving at all. Okay. So when I talk about sort of real life examples, so how do we use these cues to navigate our environment? And there's a scientist that you need to know his name, J.J. Gibson, and he took an ecological approach to perception. He wanted to study perception in the natural environment rather than just in a lab. So you had all these Gestalt people doing all these manipulations in the lab, looking at breaking apart like little bits and pieces of heuristics for specific things. But Gibson was like, okay, well, what about how we actually see things in the environment? And he was particularly interested, this is around World War II, when most flying of planes was done without instruments. So it was pretty much visually based. And he wanted to help pilots learn how to better judge landing approaches in airplanes. So he was looking at global movement of the environment and how pilots could learn heuristics to help them land more safely, right? So optic flow is going to change depending on where your focus of expansion is. So if a pilot is approaching a runway and his focus of expansion is the horizon, then everything's moving in the same direction towards him. However, if he's staring at the front of the runway, right, then the focus of expansion is here. Everything seems to be moving outward from this spot as he gets closer and closer to this spot, right? Now there's other things. There's invariant information that helps us maintain constancy, right? So we have the focus of expansion that doesn't change even though everything else is moving. We have like the size of this hangar, right? Apparent size. We have occlusion, the fact that the runway is covering certain parts of the ground. All right, so let's talk a little bit more about this angle of attack in landing a plane.
One of the most important concepts in aviation is the angle of attack. In simple terms, it's the difference between the angle of the wings and the direction in which the plane is flying. Imagine a plane that's about to land. Its nose is pointed up, but the plane is still moving down towards the runway. That difference there is the angle of attack, sometimes called alpha. If the angle gets too big, if it exceeds a critical angle of attack, a plane stalls. Airliners have an angle of attack sensor, and it's connected to the instruments and systems inside the plane. One of these is Boeing's new MCAS system on its 737 MAX series of airliners. MCAS is an automated anti-stall system. This system is the focus of the investigation into October's Lion Air crash, and experts say there are similarities between it and the Ethiopian Airlines crash. If the MCAS system senses a high angle of attack, it'll push down the nose to avoid a stall. But if the angle of attack sensor is malfunctioning and gives a faulty reading, the system could force the plane to dive, with potentially disastrous consequences.
Okay, so you can see how important optic flow cues are to trying to land a plane and have that right angle of attack coming in, right? So what J.J. Gibson did was he realized that the angle at which you were descending affected the texture gradient that the pilots were seeing. So if you were coming in too fast, descending too quickly at too steep of an angle, right, then you would see more square-like patterns, right? But if you had the right angle of approach, you would see a different type of texture gradient here. And so a system was created, a system of lights was created to alert pilots when they were on the appropriate, what's called a glide slope, or when they were too high or they were too low. And these are called the poppy lights. So here, and they're by the runway, right? And as the plane is coming in, we're going to watch a little video and let this pilot explain to us what you see and what it means based on your angle of attack here.
Now, without any navigational aids, the poppy is the only guidance you have showing if you're either too high or too low on the glide slope. Now, looking at this picture, you can see that all lamps are white. Now, you can use a little mnemonic, white on white, check your height. So you're too high on approach and you should increase your pitch down momentum momentarily and decrease power to rejoin the virtual glide slope. Now here you have two whites and two reds. Now you can say red on white, I'm alright. Keep the pitch, attitude and power setting and continue. If you would pitch down even more or decrease your power, you would slowly see all four lamps turning red. Then again say red on red, I'll be dead. So do something about it and increase your power and pitch and rejoin the glide slope because you're obviously too low. It's as simple as that, to be honest.
All right, so if we look over here at this image, we can see when we're too high, right, all four lamps are white, and look at the texture gradient, right? The texture gradient is too long. As we start to get into this glide slope, right, we have a texture gradient that would appear right for a pilot, and as we're too low, then we lose that texture gradient there. So J.J. Gibson, looking at texture gradients, looking at the focus of expansion, allowed sort of the creation of this system of lights that, depending on your angle of height, would help pilots visually navigate the right attack angle for landing. All right, so optic flow is produced by us moving through the environment. And it's also a feedback, it gives us feedback information for us to make correct movements through the environment, right? So we have this sort of perception and action relationship. So movement, the action of movement creates optic flow. Optic flow in turn informs our movement patterns, right? So we need to perceive to move, but we also need to move to perceive. So other experiments have looked at our ability to judge movement strictly on optic flow patterns. So if we were to present a static image with optic flow represented in it, and ask you to take this marker and put it where you would end up if you were moving in this image. People are very good at doing that. You're moving dead on there. What about in this image? If we gave you this image, right, you would move the marker over to somewhere over here, right? And so people accurately judge the heading within 1/2 to 1 degree, visual degree, of the correct angle based on optic flow, static optic flow information. We can improve that even more if we actually allow people to move through the environment. So here we see simulated optic flow, and you can tell when you're turning, when you're going straight, which direction that you're turning. And if we measure people's eye movements, so the cross there is where the person's looking, right? We can see that they're looking up towards the horizon. And I'll pause this for a second. If we combine the eye movements with a action task, so now you have to steer this video game so that you end up going through those two goalposts that are on the horizon. So to steer through those posts, look at where the eye movements are, right? They're tracking that, they're tracking it, and then they're lining it up so that we're going to move smoothly through that. And then finally, here we see a slalom where you're having to drive in and out, operate in and out of these posts. And what do you notice? Where is the eye always looking? It's looking at the inside corner of where it needs to go next, right? Based on the optic flow. All right, so using this driving example, we use more than just the focus of expansion, right? We're using optic flow and how optic flow is going to change based on moving straight or moving in a curve, right? So we call those lines that are moving like that locomotor flow lines, and this is going to tell us the optimal course to steer the car on. So here we see locomotor flow lines that are going to have optic flow that'll wrap around this corner. If we misjudge that, right, then we're going to misjudge the corner. So in putting people in driving simulators and looking at where their eyes are and how they're basing their focus of expansion is going to change that ocular flow line, right? So here we see person's braking and they're turning and they're heading towards their target. So going back to the example of the slalom video where we saw the person looking at the inside corner of the next target in the slalom, that's what we see with driving. So if we enter a curve, our focus of expansion shifts from being centered on a straightaway to the inside curve. And that keeps us our locomotor flow from overestimating that curve. If we were on the outside, there would be a tendency to overestimate and we would miss the curve. And so when we curve to the left, we're going to focus on that inside corner there. Here we see someone in a driving simulator and we're tracking where is their focus of expansion as they move through this road, and it's shifting from to each inside of the curve there. And so this is called a visual direction strategy. We tend to keep our body and our eyes, here we're looking at just at eyes because we're in a car, but if we were walking, we keep our body pointed at our target. And so we can measure how good we are at this, and we're really good at it with this experiment. So this is an experiment for visual direction strategy, and we have a group of volunteers at this start point, and we have a target over here. So if we have them here and they're facing this direction and we say, okay, I want you to look at your target. I want you to close your eyes and walk to your target. They close their eyes and then they turn their body at the right angle and then they walk, and they usually overestimate how far they have to go. We talked about that when we talked about jumping across gaps and why maybe it's important to overestimate our target instead of underestimate. But what's interesting is if we then ask them to close their eyes at the start, walk until we say stop, and when we say stop at this point, go to your target, they are able to tell how far they went and how what angle they should turn at, so that it'll be a sharper angle that they have to turn at. And if we have them go even further, they make even a sharper, almost a right angle here, right? So again, keeping our body, turning our body towards the target helps us with that visual direction strategy. Okay, we also use visual cues for our posture and our balance. And so if there is forward motion, things are moving towards us, then or expanding out from a focus of expansion, then we are moving forward. If we reverse that and make things move towards the focus of expansion, then we are moving backward, right? And we talked about vection illusion, right? This is the vection illusion. And in fact, if we take a false room and move the whole room backwards, we will compensate with that and try and move forward to the point we might even fall down because the room's not actually moving. It's sort of like mashing on that brake because you feel like you're moving backwards even though you're standing still. All right, so we also use expanding focuses of expansion to avoid collisions with other objects, right? And so if an object is expanding in a symmetrical way towards us, right, then that indicates that it's coming in a straight line directly at us. If it's asymmetrical, then our vision can judge how much how far away that object is going to pass by us. Right? So that measurement of expanding edges is called tau, and it's a calculation that our brain does by looking at an object, taking sort of a snapshot of an object at different points in time very rapidly to see is it symmetrical or not symmetrical. So if you look down here in this white space, I'm going to have a square zoom out, and that zoom effect is simply created. It looks like the square was far away and it came towards you. That effect was done simply by taking a small box and expanding the edges symmetrically. So it gives the illusion of movement, right? Birds have to use their visual system even more than we do because they're moving in 3 dimensions when we typically are only moving in an XY pattern. We're not typically moving up and down like birds that can fly. And there are diving birds. The Gant diving bird has to dive from a great height, and then right before it goes in the water, if it doesn't fold its wings, it would tear its wings off. So it has to judge the collision with the water and wait till just the last spot to fold its wings in. And so the question researchers wanted to know is, does the gannet do a tau calculation to time the folding of its wings? And they could observe this if they time the height, and they look at the height and time the speed, and then look at when does the bird fold its wings. And doing that, they found out with greater height, they folded their wings sooner based on a tau strategy, a tau calculation strategy. So analyzing this film of birds diving from different heights suggested that yes, their brain is doing this tau calculation. Sometimes we want to collide with objects. So think about a outfielder that needs to catch a fly ball. There's a big outfield. There's only 3 people out there, and you have to cover a lot of ground in order to get to wherever that ball is going to go. So one way to do it would be to have an algorithm, right? Determine ball speed and trajectory and calculate a landing spot. But everything's happening so fast. It's too fast to do that kind of a calculation. So when we can't use an algorithm, what do we use? Heuristics, yes, heuristics, right? So it's too hard to determine the factors. So there's actually a heuristic that outfielders learn that they start moving. So they initiate movement as soon as the ball is apparent that it's going up, right? And it's going to come in the outfield. And they are moving so that they keep that ball traveling in a linear pathway in their field of vision as they're running. And they're having to make movements immediately, and they're having to make corrections during that run to hopefully get to where the ball's going to land just before the ball gets there. All right, so this is a lot of perceptual evidence. What about physiological evidence? And it turns out, again, birds have to be very careful that they don't collide with things when they're flying. That would be fatal, right? And so pigeons actually have collision-sensitive neurons in their pathway for space and movement. So here, we're recording from these neurons in a pigeon's brain, and on a screen, we're showing them a checkered ball that's expanding in a symmetrical way towards them, indicating it's going to hit them, right? And it doesn't matter if we change the size of the ball, a 10-centimeter ball or a 30-centimeter ball, and keep the speed the same. This neuron starts firing just right at 1 second to collision. It's warning the bird, you have 1 second to change course or you're going to get hit, right? Or if we keep the size the same, 30 centimeters, and we change the speed of the ball, make it more than twice as fast, it's still, this pigeon's still able to have that neuron fire that says you have 1 second to change, right? So obviously this ball moving at twice the speed is going to be twice as far away at 1 second. So it's not even, that it's this close to you, but it's actually a timing situation. Monkeys, we can measure optic flow neurons in the MST, the middle superior temporal area. So MT, direction specific movement, MST, optic flow and it's direction specific as well. So here we see a neuron that's responding to symmetrical focus of expansion and does not respond to optic flow in a curve. And we can go find another neuron that fires best to optic flow in a curve and then is not selective for the focus of expansion optic flow. If we damage the middle superior temporal, it inhibits the ability for us to move in a fluid way. So here we've trained a monkey to follow a target with his eyes. And so pre-surgery, pre-lesion, the target starts moving. The monkey recognizes it's moving. His eyes do a saccadic eye movement to catch up, and then it does a smooth pursuit movement. When we lesion MST, the monkey has trouble following that optic flow. So we get the saccade, and then we have a bunch of little saccades like trying to catch up or overshooting that target. Here we happen to have a human that had a stroke or had trauma in the MST, and they show the same thing. Smooth pursuit target, and we have this saccadic eye movement sort of catching up to the target. All right, so we've talked about V1, V3, middle temporal, middle superior temporal. Now we're going to talk about anterior inferior parietal, AIP, anterior inferior parietal. And what we find in anterior inferior parietal is starting to become a mixture of both vision and motion and motor system, right? So visual motion, motion perception, and action. So there are motor dominant neurons. So we've told a monkey, we've trained a monkey to push a button. And then we put them in the dark and say, push the button. So there's no visual cues. There's simply motor cues. And we see that this neuron fires when he pushes the button. These other two neurons don't fire. We have visual dominant neurons. So now we tell the monkey, just look at the button. Don't push it, just look at it. So no motor signal. Now we have a neuron that fires to vision, right? Then we have a combination of vision and motion. So we say, okay, now push the button in the light. The motor system is activated, the visual system is activated, and a third neuron that was not activated by either one, right, a perception and action neuron, now is firing. So this is physiological evidence of this reciprocal, this relationship with perception and action together. Moving on up further in the brain to the premotor area, we see specialized neurons in the premotor area. So remember, premotor area is where we have sort of central pattern generators like program movements. And so here we see a neuron in this monkey. So let's look at the center one. That is going to fire when the monkey picks something up. It's sort of the how do you pick something up neuron. And there are neurons in this area called mirror neurons that respond both to that monkey doing the action, but also seeing a human do the same action. That neuron fires like a mirror, right? If we now use a tool to pick up that thing, that neuron is not active. That's too different of a motor movement, right? So what would the usefulness of a mirror neuron be? Why would a monkey want a neuron to fire when it sees someone else do something? Yeah, I hope that you said observational learning, right? This monkey is learning that, hey, that thing where I reach out and pick something up, if I see someone else do that, I get excited because that's the same thing that I do, right? Observational learning, right? We're reinforcing that. We can have someone else's action reinforce our ability to do that. All right, we've talked about a lot, right? And so with motion, it's a complex world, right? I want to point out in the figure caption that this is a simplified diagram showing how information flows out of MT and MST to other areas of the brain. We didn't even talk about LIP and VIP, but just looking at the pathway that we talked about, right, flowing out of here into specialized pathways in this dorsal stream, right? So we have direction-specific neurons, optic flow sensitive neurons flowing into that anterior parietal area where we're getting now a combination of motor signals. So it says that no, most arrows go both ways, right? So motor signals coming here, visual signals coming here and meeting up to now become an action signal. And then mirror neurons in the premotor area responding to visual stimuli, even though they're motor output cells. All right, stick with me. One more experiment I want to talk about. Humans and perceptions and what influences them, some top-down influences. So there's a psychologist that was at UVA, and if you've ever been to University of Virginia campus, it's very hilly, lots of hills. And Prophet is this professor who was interested in visual perception. And so he had 300 undergrads judge the slant of some hills on campus. And he actually measured the angle, so he knew the correct angle, but he had them do some estimates of what those hills were. And he had them do three different things. First, he had them give a verbal degree estimate. So I think that is a 10-degree hill, right? Then he had them do a visual estimate where they took this disc and they adjusted the angle of the disc to where they thought it visually matched the hill. And then he had them do a third estimate with this contraption that he built where they would put the palm of their hand on this wooden plank and then adjust the wooden plank to the angle that they thought the hill was. So we'll do our last ed puzzle question here, and I'll say, which of these three do you think was the most accurate? The verbal estimate, the visual estimate, or the haptic estimate? So without vision, touch only. All right, for those of you that said haptic, you are the correct winners. No one's a loser. I mean, you're not getting it correct, right or wrong for that, obviously. But haptic was the best answer, and look how close haptic was, right? So when we have to do an action, right? When we have to do an action like move that board, right? We get it the most correct. It's like the visual direction strategy, right? And notice that for both verbal and visual, once again, we overestimate things. Now, here's the interesting thing that Prophet found out. Those estimates that are off, that are overestimated, they increased under certain conditions. So if he made the subjects go run 3 laps around the track and then do the estimates when they were tired, right, the hills became even taller, even bigger angles, right? And if they were standing on top of the hill looking down, which is a scarier proposition than standing at the bottom of the hill and looking up, right? When you're on top of the hill, you judge it as even steeper, right, than if you're at the bottom. And then he even put subjects in heavy backpacks. And when they were wearing heavy backpacks, they judged that the hills were steeper, right? So our perception is directly influenced by our perceived difficulty of an associated action. So if you're going to make me go up this hill in this heavy backpack, yeah, that hill looks a lot steeper than if I'm not fatigued and I'm not wearing a heavy backpack. All right. So there's your review points. This is it for vision, right? We're going to take Thursday off from class. I'd like you to use that time to really study hard for your vision exam, which will be next Tuesday, hopefully, if we're in person. Hopefully we will be. Hopefully the numbers are going down, testing's going up. And so in the meantime, if you have questions, please reach out to me. I'm happy to answer them by email. I'm also happy to schedule a Zoom meeting with you to answer questions or explain something that you're having a hard time with. And we will have review sessions next week. We will have review sessions. So stay tuned. This is it for this week. and this will be due by Wednesday at midnight. And I'm going to start working on your lab reports. I've been recording all of these lectures, and so now I'm going to focus on trying to get those reports back to you. Make sure you're signing up for a time to do the color vision lab. I've seen some of you in there. And stay safe and stay well.